Recall that when we spoke about atmospheric pressure, we said that at sea level, our atmosphere is able to create a pressure that is equal to this quantity. So the molecules and atoms that compose our atmosphere create a pressure equal to 1.013 times 10 to the 5 newtons per meter squared. Now let's suppose we examine the following lake. So the surface of the lake is at sea level, and the height from the surface of the lake to the bottom of our lake is h. Let's suppose we want to calculate the fluid pressure inside our lake. So we want to calculate the fluid pressure at the bottom of the lake. So not only do we have to calculate the pressure inside our lake due to the volume of liquid above it, but we also have to incorporate the fact that there's not only liquid above that point, but there's also this entire sea of air molecules. So this atmosphere creates a pressure which will exert a pressure onto our liquid, and this will in turn create an additional pressure at this point. And to actually find the pressure at the bottom of the lake, we have to sum up our atmospheric pressure as well as our pressure due to the volume of liquid found above that point. Now, this principle is known as Pascal's principle. Pascal's principle states that if an external pressure, in this case our atmospheric pressure, is applied to our confined fluid, in this case our lake, the pressure at every point within that fluid, within our lake, increases by that external amount. Now, a very common device that utilizes Pascal's principle is the hydraulic lift. So the hydraulic lift utilizes the Pascal's principle by turning a small input force into a large output force by increasing the area. So this is one example of a hydraulic lift. So this is our input, this is our output. So we apply a pressure P1 to this area A1, and because this inside section is a fluid, the pressure will remain undiminished and go through the entire fluid. And so the pressure that this area feels is the same pressure that this area feels. So P1, the pressure here, is equal to P2, the pressure here, because of Pascal's principle. Now, notice that the area of this piston, A1, is smaller than the area of this piston, A2. And because P1 is F1 divided by A1, and P2 is F2 divided by A2, where A1 and A2 are the respective areas, and F1 and F2 are the respective forces, if we increase the area of this piston, that means we also have to increase the force that this piston feels by the same proportional amount, because P1 is equal to P2, and that means the ratio of force 1 to area 1 is equal to the ratio of force 2 divided by area 2. So as long as these two quantities remain constant and we increase A1, well then F2 has to increase by that same amount. So if we increase A2, F2 also has to increase by that same amount. Now we can rearrange this equation and we get the following result. The output force divided by the input force is equal to the output area divided by the input area. And this quantity, F2 divided by F1, is known as our mechanical advantage. So let's look at the following example. Let's suppose a car uses hydraulic brakes. If the area of the brake pedal is 0.01 meters squared and the driver applies a force of 20 newtons onto that brake pedal, calculate the output force assuming the area of the output section is 0.1 meters squared. So we essentially take this equation and we want to calculate F2. We want to calculate the output force. So we bring F1 to the right side and we have the input force multiplied by the ratio of the areas. So we plug in our quantities 20 newtons, this becomes 0.1, and this becomes 0.01. So this ratio becomes a 10. 10 times 20 gives us 200 newtons. So we see that because the area of the output piston increased by a quantity of 10, by a proportion of 10, that means the output force also has to increase by that same proportional amount. So it goes from 20 to 200.